Okay, so let's have a look here. We've got a mug of coffee that's cooling down. Okay, so we've got the temperature of the coffee given to us by this exponential function. We can see that with the negative constant there, it suggests we have a negative exponential. So our graph will look a little bit like that. Okay, so what is the initial temperature? Initial temperature. Okay, there's the keyword initial. Initial suggests that T was equal to 0. So if I put T equal to 0, the capital T is equal to 20 plus 75E 062 times 0. Well, e to the 0 is simply 1. So the temperature of our coffee is 20 plus 75, which is 95. Now, don't forget that typically our modeling questions are going to have calculator available. So really the first thing we do is probably define our function on our CAS and just work out F1 of 0 perhaps. To what temperature will the coffee cool if left unattended? So in other words, time is just going on forever. So if we sketch the graph, it's probably more obvious. We know that at T equal to 0, our temperature of the coffee was 95. That 20 there suggests that's what our graph has been moved up by, 20 units. So in reality, our graph is going to look a little bit like that. So just from the asymptote, we can see that the temperature of the coffee cools down to as far as 20, or room temperature, which kind of makes sense. If you like, we could just let T equal a big number. And if I do that, T is equal to 20 plus 75 e to the negative. Well, that's going to be 62 or thereabouts. And e to the minus 62 is approximately 0. So we can see that our graph or our coffee does approach the temperature of 20. How long does it take for the coffee to reach a temperature of 65 degrees centigrade? So here we're saying the capital T is 65. So I want to solve 65 equal to 20 plus 75 e to negative 0.062 t. So there's your 1 mark there for saying the math that you want to use. And then we're going to get t equal to, in our case, we'll get t is equal to 8.359 minutes to 2 decimal places. We'll say equal to 8.36 minutes. Okay, so now Manoj comes back and at t equal to 8.36 to reheat his coffee. So at T equal to 8.36, the temperature of our coffee is, what is it? It's 65 degrees centigrade. And also, our coffee approaches 85 degrees centigrade. So then that's sort of, so as T approaches a big number, capital T is equal to 85. So again, that big number of e to the negative 0.05 t, so if we look at t is equal to a plus b e, that negative 0.05 times a big number, that really approaches 0. So in other words, A, or the temperature, if you like, T approaches A, and therefore A is equal to 85. So I know T is equal to 85. So therefore, I can write over here, the temperature of 65 is equal to my A value of 85 plus some B e to the negative 0.05 times the T value of 8.36. So if I solve that on my CAS, I'll get, okay, so you can see here, I've gone to the calculator to solve my equation, and we can see a couple of things. obviously, there's my initial temperature, 95. The value approaches as T gets bigger is 20 degrees. But you can see a little error there. It's not 8.36, it's 8. Let's get rid of that. So it should be, what's that, 8.239. So we'll call it 8.24, which means, let's just change that to an 8.24. And we can see on the calculator I've done that, and we get B is equal to negative 30. Doesn't really give us a degree of accuracy. We'll give it negative 30.2. Negative 30. Oh, it's not degrees, it's just a constant. So the B value is negative 30.2, the A value is 85. Okay? Go back, yes. So to show our cooling and warming, let's hope I remember our values. My original function, okay, had an asymptote at 20. So we'll call that 20 there. So we'll call that, well, probably should be T equal to 20. The initial temperature was 95 degrees and it cooled down to, so I'm going to call that 20, 40, 60, 80. Cooled down to 65, didn't it? So it cools down to about there. And we'll call that 8.36 minutes. So that's my time. Then my next function came in. Okay. Now it was heating up. It was a negative, heating up to a maximum temperature of 85, I think, from memory. Let's check 5. So if that's 80, 20, 40, 60, 80, 85 might be there. So it's got an asymptote at T equal to 85. And it's going to increase that way to a maximum. Okay. Sketch the graph showing the temperature of the coffee during its cooling and warming stage. So I reckon that covers that. Okay, so let's have a look. Biologists and experiments determine the conditions that affect the growth of bacteria that affect. Oh, Jesus, a few typos that affect the growth of bacteria. Her initial experiment finds the growth of the population of bacteria is modeled by the rule n is equal to 22 times 2 to the t, when n is a number to bacteria up to t days. How long will it take for the number of bacteria to reach 2816? So 2816 is the amount of bacteria. So clearly I need to solve 2816 equal to 22 times 2 to the t. Okay, so once we've done that, I can't see no reason why we can't use our CAS for this. We could obviously 2 to the t will equal 2816 on 22, but it's just as easy to go straight to the CAS and t will equal, the CAS will get t equal to 7 days. What will happen to the number of bacteria in the long term according to this model? Well, if we consider that what the graph of this is, it's just an exponential that looks like that, isn't it? So in the long term, the number of bacteria will continue to grow unchecked, and increasing indefinitely. We'd like to be able to say that increases to a infinite amount, but there's no infinite, so it just goes on forever and ever. Righto, the biologist changes the conditions. The growth of population is modelled by the rule n equals 66 over 1 plus 2e. Show that in both of her experiments, the biologist used the same initial number of bacteria. Okay, so for the first experiment. So n was equal to 22 by 2 to the t. At t equal to 0, it's equal to 22 times 2 to the 0, which is equal to 22. For the second experiment, n is equal to 66 over 1 plus 2e negative 0.2 times 0, which is equal to 66 over 1 plus 2, which is equal to 22. Therefore, same initial pop. Quick look, what's our model? 66 over 1 plus, don't know what the 66 represents. No, it's not thousands, it's just 66. What's next? What will happen to the number of bacteria in the long term according to her second model? So B. So n is equal to 66 over 1 plus 2e to the negative 0.2t. So we can say as t gets really big, e to the negative t gets really close to 0. Okay, so we can just see that from the graph. Remember, our negative exponential just goes down that. All right, so therefore, n will approach 66 over 1 plus 2 times 0, which is just equal to 66. So that's how many we'll end up with. Okay, let's have a look at example 24. Carbon-14 don't measure the amount of active carbon-14 in fossils. This can be modeled by the relationship blur. Q is the amount of milligrams of carbon-14 currently present in the fossil of an organism. T is the time in years. Q naught is the initial amount in milligrams of carbon. A fossil shell initially has 150 milligrams, so therefore Q naught is equal to 150. We were told that. Okay, so after 2,000 years, so at T equal to 2,000, I'll have Q equal to 150 times e to the negative 0.000124 times 2,000, and we'll go straight to our CAS, and therefore Q is equal to 192.219. I'll show you the CAS printouts just when I get to the end of the problem. Find the number of years it would take for the carbon-14 in the shell to be halved. So it's what we call a half-life. So really what we're saying, if we started with 150, I want to solve how long it takes for there to be half as much. So I want to solve there to be 75 equal to 150 e to the negative 0.000124 t. Solve that for t. So just to highlight, divide 150 equal to, yeah, and you can see that's where our half is. Using our CAS, t will be equal to, I can't remember, 5,000, I'm going to put the print, 5,590 years, I reckon it was. There is another little error. When I get the printout, on my calculator, I didn't have the negative sign in place. So I think that's, I'm not too sure if that's the right number or not. We'll check that answer anyway in a minute. Okay, let's moving on, and then I'll give you the CAS printout. Suppose the amount of carbon-14 in the shell, carbon-14 in the shell is Q naught on N. Find an equation relating N to T, and find how long it will take. So the amount of carbon in the shell is Q naught on N. So what does that mean? So that's the amount of, so we've got Q naught on N is equal to Q naught e to the negative 0.000124 0.00012 T. Hence, find an equation relating N to T. Well, obviously our Q naughts cancel. So I get 1 on N is equal to e to the negative 0.000124 T. If I flip both of them up, N will equal e to the positive 0.000124 T. So there's a relationship between N and T. Hence, find how long it will take before the amount of carbon-14 in the fossil shell is given by Q0 on 10. So clearly in this case, N is equal to 10. So let's use our CAS to solve. 10 is equal to e to the 0.0000124 T. Therefore, T will equal. You see here from our printout, if we solve 10 equal to that expression, I'll get 18,569 years. And you can see there that for the earlier question at 2000, the amount of substance present is 117.054 milligrams of carbon, okay?